Thank you for the introduction. Good afternoon, everyone. I'm an electronic engineering student from UniMelb. Today, I'll give a presentation for our group's recent findings on the next generation lab-on-a-chip deploying cell metabolism sensing. So it has been well known that in conventional drug discovery method, which needs 3 stages: cell culture studies, animal research, and 3 phases clinical test. In recent published FDA in 2022 said striking preclinical tests and inserting non-clinical tests, and then lists several complementary animal testing model where the macrophysiological system is one of these. The macrophysiological system has advantages of reducing the need for large numbers of animals, reduce the cost, more physiological relevant, high throughput screening, accurate prediction of drug efficacy, and even benefit personalized medicine. So our group goal is to build a next generation lab-on-a-chip to improve the human physiological relevance in detail in 5 sectors: human relevancy, advanced culture, miniaturization, throughput, real-time cell monitoring system, and lastly, integrated previous 4 elements to build a feedback control system. So the first part, understanding the cell shape and stiffness is important as it can influence different cellular functions, including migration, differentiation, and gene expression. So our group member Chao Hui has developed a technology which can manually control the cell shape's aspect ratio, as shown in the left-hand figure here, from 20 to 1 under controlled stiffness 40 kilopascal. And in the right figure, the F actin element mean intensity changes between the circular cell shape and the elongated cell shape. This highlights that the cell shape will influence the cellular process. Having improved the human relevancy mechanically, we're also trying to improve the human relevancy biochemically. The first part is the medium composition developed by Tina Chen. In the conventional medium compared to the human plasma, it has excessive concentration of amino acid and glucose, while lack of some key elements, such as vitamins, trace elements, and fatty acid. Research have shown that such unphysiological medium composition might distort cell metabolism. In our proposed medium, Melbourne medium, which has a component and concentration close to ultrafiltered human plasma, and our research on cancer cell compared the Melbourne medium versus conventional medium shows that several fundamental cell information changes in Melbourne medium. And we're also worried about the nutrition delivery. In conventional nutrition delivery method, it was working under a static culture system without flow, and which may generate waste accumulation. In our multiplex superfusion system developed by Brian Gould RPM square, which can provide constant flow with continuous nutrition exchange and waste removal. This system ensures our Melbourne medium working on the physiological range, while in conventional medium, it exacerbates the unphysiological level, stay in a hyperphysiological range. And here is our superfusion system set up. We place the RPM square close to the cultural vessel in the incubator, and at the upstream of the RPM square, we connect the selection valve and connect to different drug inputs or media supply. And they are stored under 4 degrees to mimic the distortion of the drug efficacy and to ensure the long-term experiment. I've also validated the secondary entrainment by the RPM square. The secondary entrainment is a sleep-wake circle synchronized with the 24-hour light-dark circle of the environment, where the cortisol can regulating the secondary entrainment. As shown in the video here, with RPM square daily injection of the cortisol, we can observe the mouse embryonic fibroblast per 2 look, which is a circadian biomarker. It changes circadianly in 7 days, while in the other compared group, it doesn't. This result promotes our RPM square from prototype in publication to minimum viable product for user engagement. So understanding the cell culture dynamic metabolic changing is also important. As an engineer, I was trying to monitoring the system into 4 sections: nutrition, metabolites, environmental factors, and endocrine system. And here is our key sensor, the electrochemical aptama-based sensor. The aptamer are short single-stranded DNA or RNA molecule. So we coated a monolayer of the aptamer on the gold electrode, and the other end connect with the redox reporter methylene blue. So with the change of the concentration of the target analyte, it will change the structure of the aptamer. And the distance between the redox reporter and the gold electrode will change, and under such way to influence the electron transfer rate. And this is a reversible process, and it has other advantages like ease for synthesis, sufficient selectivity, high stability, and small size. Our cooperated group, Kevin Plexel group, they have already developed a large variety of aptamer sensors for human plasma monitoring. We're planning to start with the phenylalanine sensor and moving it into the cell culture system. So, how to detect such electron transfer rate differences? We connect a 3-electrode structure, working electrode gold, counter electrode platinum, and the reference electrode silver chloride. So we perform a square wave voltammetry between the working electrode and the reference electrode. And we measure the current between the working and counter electrode. And here is the measurement example. At high concentration of the target analyte, the peak current differences is higher than the low concentration of the target analyte. So when we change the concentration of the phenylalanine and calculate out the signal-change ratio, we find a perfect Hill-fitted relationship between the concentration of phenylalanine and the signal-change ratio, especially in our interesting physiological range. Moreover, we surprisingly find that when we change the pH of the measurement solution, the peak potential, which is the peak current indicated potential, shift left and right. We want to further investigate whether we can use the peak potential to reflect the change of the pH. The answer is yes. We find a perfect linear relationship between the peak potential change and the pH change, and the pH does not have any hysteresis effect on the measurement. To further dig in whether it is a universal idea for such dual sensing ability, we coated another 2 aptamer sequence, one with doxorubicin aptamer, another with L-tryptophan aptamer. Both shows a great linear response with a change of the pH. Furtherly, we gathered 1,000 noise data points from either Melbourne medium or the working buffer and fitted it into a Gaussian distribution to predict the resolution in pH on one single scan. So from the result, we can ensure at least 0.09 pH accuracy, and this could be even improved by mathematical way with a continuous measurement. As we can see, the noise mean is really, really small, close to 0. Moreover, we want to build a multi-electrode measurement array. So we want to figure out whether the aptamer electrodes to aptamer electrode has interaction to each other. So here we coated 2 electrodes with 2 different aptamer. One is L-tryptophan, another is the phenylalanine. And we titrate the phenylalanine and the tryptophan. So in our interesting physiological range, there is negligible influences between the sensors. And since in the future, we're trying to integrate the sensor system with the flow rate. So we are thinking and investigating whether the flow rate will generate any distortion in the sensing. So the answer is no, either on the pH measurement or the target analyte measurement. And next, I want to introduce the reference electrode we use in our system. So as previously mentioned, we are building a 3-electrode structure. So silver chloride wire is one of the reference electrode. So the conventional wire, it is hard for sterilization, and because of leaking of the silver iron, it might generate cytotoxicity to the cell environment, and it has low shelf life. So in conventional reference electrode, it covered the silver chloride wire with glass tube filled with 3 molar sodium chloride, and the other end connect with porous freight. However, since it's a porous freight, so it still has the problem of the leaking of the silver iron and might generate cytotoxicity. In our liquidless reference electrode, instead of like sealed with porous freight, here we sealed with a platinum to ensure there is no leaking of the silver iron. Under such way, also it's easier for sterilization and improve the miniaturization and improve the longevity compared to the pure silver chloride wire. And when we take the open circuit potential measurement, compare with the commercial reference electrode, its potential is as stable as the commercial reference electrode. And next, to validate our sensor, we start the cell metabolism measurement. We perform a 3-day measurement, and in day 0, we start the sensor fabrication and the cell seeding to ensure the fully confluency, and the component sterilization to ensure there's no contamination. And the cell line we use is A549 in incubator on the static condition with Melbourne medium. And in each days, we take 15 minutes sample interval with 5 hours continuous reading. And between each days, we take the cell microscopy to ensure the cell's health state and compare the cell well with sensor and without sensor. And here is a cell image result. If you compare the cell image with sensor and without sensor in each days, there's no significant differences between either the cell morphology or the cell viability. That ensure our sensor's biocompatibility and non-cytotoxicity. And based on the sensor reading result, from the result of the final animal reading, so in day 1, it can stay a relatively physiological range. However, since cell deviation or growth need to consume nutrition, at day 2 and day 3, it's already down less than 1 micromolar, stay in an unphysiological range. And based on the pH reading result, so since cell consumption nutrition, it will generate some cellular byproduct like lactic acid, organic acid. If the cell consumption rate exceeds the fresh media supply rate, which might generate acid drift as shown in our sensor reading here. This data support our sensor's measurement ability to reflect the cell metabolisms. Also, it highlights that we might need such real-time monitoring system to ensure that the cells are working under healthy conditions to improve the drug discovery efficacy. To sum up, our dual EAB pH sensor has 4 advantages. Firstly, it's small size. All the electrodes are less than 1 millimeter sized, and it has fast response time. For the pH, it only takes less than 1 millisecond for the measurement of pH and less than 10 milliseconds for the second analyte measurement. And it has great multiplicity. We have the first universal analyte, pH, and the second analyte depends on the coded aptamer sequence. And from previous research, it shows at least greater than 3 days biocompatibility. And in the future, we're trying to standardize this system into a more mature product, which will consist of the well lead, which is reusable, fully sealed, sterilizable, and the plate, which is consumable, and the plate place different aptamer sensor array depends on the printed gold electrode. And lastly, we integrated previous 4 mentioned elements, start with the pump and the valve with the nutrition and media supply connect to the cell well, and reading the metabolite, nutrition, and environmental factor back to the microcontroller and further precisely control the media level, flow rate, and nutrition. I want to express my thanks to my supervisor group Ranges, Alastair, Kevin, and their group members who support my project. And especially thanks Dr. Brian Gao, Tina Chen, and Shaohui Li, who support part of my slides, and they will also do poster presentation in these following days. And thanks for everyone's listening. We're looking forward for everyone's support and suggestions.
Thank you so much. Okay, so we're taking questions. That's quite far, but I'll get to you.
Thank you for your presentation, Gonçalo Gamboa, FDA. I'm interested in your Melbourne media. Were you able to steer away from fetal bovine serum as one of the ingredients so that we actually go towards truly non-animal approaches, or can you speak to what's in that medium?
Yeah, thanks for your questions. I cannot hear very clear, but I think it's related to the Melbourne media. So in this afternoon, we'll give a poster presentation related to Melbourne media, and I'm an electronic engineer. I'm working on the sensor part. So we are looking forward to have a more detailed discussion about the Melbourne media during the poster presentation.
Okay, that will work.
Thank you.
Thank you.
Yeah, thanks for your presentation, very nice. I have a question about your electrodes because I saw in the results session you have plot some kind of potential and current plot, and I didn't see that reference on the potential. So you don't have some kind of potential versus something. So do you do some kind of calibration for your electrodes, electrochemically calibration for electrodes? Or your sensor is just calibration free to use?
You mean for the standardized product or for the cell metabolism measurement system?
I mean for the electrochemical sensor.
Yeah, so under a standardized fabrication process, we can achieve like no calibration free, but we suggest to, if we want to achieve a high accuracy measurement for the cell metabolisms, so we did the calibration before we start the measurement. Yeah.
Okay, thank you.
Thank you for the presentation. I was wondering, apart from the images to determine biocompatibility, have you carried out some other type of analysis of like ion presence in the medium and so on?
Yeah, so thanks for your questions. That's also in our future plan. So that's the first proof of concept to make sure our sensor has no contamination or not obvious cytotoxicity on this like cell culture system. And in the future, we're trying to improve and further prove that like a more like advanced method to prove that there's no like cell variability influences on the culture system. Yeah, that's in our plan.
Thank you very much. I think with this we conclude the session. I would like to thank again all the speakers of the session. And I wish you a very good continuation of the conference. Thanks again.